Okay, now that we've had a chance to look at the real number system and we've had a chance to look at the imaginary number system, we're going to take a look at the complex number system. Okay, complex numbers. Now, as we mentioned before, for those that are kind of a visual, what's happening here is we have a real number. We have the whole real number system that include rationals and irrationals. And again, you've learned how to add, subtract, multiply, divide, do powers, roots, graph them. We've spent a lot of years looking at the real numbers. Then the last lesson, in one day, we looked at a different number system called the pure imaginary numbers. Okay. Well, now we're going to combine these together, the real numbers and the imaginary numbers, and when they are combined together, we create what are called complex numbers. The complex number system. So the complex numbers sort of has like two parents. They have the real number part and they have the imaginary number part. So complex numbers look like the following. Sometimes we'll use the letter Z to represent. We will definitely do this in pre-calculus. But a complex number has two components, has two terms. It has a real number component. It always comes first. And then we have the imaginary component, which always comes second. Okay? So it always has to have two terms in order for it to be considered a complex number. If either one of these terms is missing, we insert a 0, as we would when any other time. Okay. So now let's take a look at them. Well, just like any number system, we're going to start off with what they look like. And your textbook doesn't really go into this, so I want to show you what the graphs look like before we look at the operations. All right, so here's what we're going to explore. With complex numbers, here's our goal for today. Where you took about 7 years of education, we're going to take about 30 minutes. You took about 7 years to go through real numbers. You learned how to graph them on a number line. You learned how to add and subtract these numbers. Then you moved on and you learned how to multiply and divide numbers. And of course, with multiplication and division come powers and roots. Now, to be honest with you, we can do some of the powers now. We can raise this to a second power, but I won't go higher than that. And the reason is both of these, in order to take powers and roots of complex numbers, we're going to be using de Moivre's theorem, and that's a pre-calculus topic. So we will do most of this in pre-calc, because we're going to have to change number systems in order to actually find those powers and roots. Then we'll convert them back. But we will do powers of 2. Okay? So let's take a look. Let's start with graphing. Here we go. I'm going to ask you to graph the following numbers. I'm going to call the first point A. Let's call it the complex number 3 plus 4i. So this is how we graph it. Notice it's made up of two parts, a real part and an imaginary part. The real part comes before the imaginary part always. So when we graph this, since we have two parts, we're going to graph this on a two-dimensional plane. Okay? So we're going to graph it on the two-dimensional plane. Now, the reason your teachers hopefully have been nagging you for years to label your axes is we're not in the real number system anymore. We've now switched to the complex numbers, which are made up of real and imaginary. Since the real numbers come first, that's what goes along the x-axis. Since the imaginary number comes second, that's what goes along the y-axis. Whoops, a little bit off the screen. Let me bring that word down. I apologize. So this is the imaginary axis. Okay, now we'll abbreviate here in a moment. Now, the rest is similar to what you've already done in the real number system. As I mentioned in class, these are the idea of different number systems. They have similar operations, they have similar qualities, but they're not identical. So although the real numbers may have similar operations to imaginary, they're different systems. Kind of like planets. Planets are similar in that they're spherical. They orbit around the sun. They may have different seasons, climates, so they may have similarities, but they're very different planets themselves. Okay? So in this case, our complex number system, we have a real number and we have an imaginary number. So the real number is the number 3, the imaginary number is the number 4. Since I go in order, real and then imaginary, the real number is positive 3, the imaginary number is positive 4, and so I put a point here that represents, I just called it A for this one, that represents the number 3 plus 4i. So we're going to do it again. I'm just going to switch colors. Let's graph the number. I'm going to call this point, point B. Let's graph 2 minus 5i. Well, again, 1, 2, 3, 4, 5. The real number part is 2. The imaginary part is negative 5. Not negative 5i, just negative 5. So I'm going to go right 2, down 5, and that's point B. And that's it. So yes, it coordinates with what you've done on the XY plane. So let's try a couple more just to solidify this. Let's say I have you graph the point negative 2 plus I. That's going to correspond to the point that is negative 2 in the real direction, positive 1 in the imaginary direction. So I'm going to go left 2, up 1. And I'll call that point C. And then just to finish it out, I don't know why I put parentheses around it, just to finish it out, now let me ask you this. What if I gave you negative 3i? And that's all I gave you. And I wanted you to graph that. Well, we need to have two parts. We need to have a real part and we need to have an imaginary part. So this is exactly the same as 0 minus 3i. There was not a real number written down, so we just inserted 0. So that would coordinate to the point 0 minus 3, and so I put point D right there. And so that's how we graph complex numbers. That's it. Pretty nice. Okay, so that took care of graphing. Done. Now this is a different number system. So let's work our way through adding and subtracting. Okay, adding and subtracting. Well, you already know what to do. You do. The concepts have not changed. Let's do this first. Actually, let me pick some numbers in the book so that if we ever have questions, we can do that. So let's take a look at number 2. Number 2 in the book says 3 minus 4i plus negative 5 minus 2i. Well, you guys, I have total confidence in you. You already know what to do. We know that when we add, we combine like terms. That concept never changes. So in this case, if we're combining like terms, we need to combine the real number parts and we need to combine the imaginary number parts. This number system is similar in that most of the field properties work, but we can still use the commutative and associative property. So I'm going to put the real number parts together. And then I'm also going to combine and add the imaginary parts together. And then you just do what you already know how to do. And this will give me 2 minus 6i. And we always put the real number before the imaginary number, because the real number axis is the horizontal, and that always goes before the vertical axis, which is the imaginaries. Okay. I don't know if I need to do another one, but I will. Here's number 6. As I said, your prior knowledge and experience is going to help you. Now, number 6, we have a couple things going on. It says 2 times negative 1 plus 6i minus 3 times 2 plus 5i. So again, we're going to work with prior knowledge. Your instincts already know what to do. Because the 2 is out front, because the 3 is out front, we're going to distribute and then combine like terms. There we go. And then I could ask you to graph your solution. So I think we've got adding and subtracting. We even put a little bit of multiplication in because we did the distributive property. Now let's move on to, let's see. We multiplied a real number by a complex number. Let's multiply a complex number by a complex number. So we'll take a look at 14. Actually, before we do 14, I want to do 12. Because I want to talk about what 12 looks like. 4 plus I, 4 minus I. In chapter 4, we called these the sum and difference of 2 terms. Okay? Sum and difference of 2 terms. But earlier in this chapter, we said, well, instead of calling them the sum and difference of 2 terms, we called them the conjugates. Conjugate pairs. Okay? Those are conjugate pairs, the sum and difference of 2 terms. We also already know what's going to happen when we FOIL them out. We already know that when we FOIL these, and of course you can always work it out. Your first term is going to be 4 times 4. Your inside term is 4i. Your outside term is negative 4i, so they always cancel. And then if you remember, conjugate pairs always left us with the difference of 2 perfect squares. The first term, 4 times 4, the last term, I times I. But we're not finished yet. We're not finished because we know what I squared means. Remember, I squared is the same as negative 1. So this actually becomes 16 minus negative 1, because I squared is negative 1. So you'll notice what ends up happening. This ends up, instead of being the difference of two perfect squares, this ends up being the sum of two perfect squares. And so our final result when we simplify would be the number 17. So we have eliminated the i's completely. We have eliminated these square roots of negative 1 completely. So make a note of it. Write something in your notes. Anytime you multiply complex conjugates, you're always going to get a number. So the product of complex conjugates yields the sum of squares. Sum of squares. I almost ran out of room there. Sum of squares. Okay, that's going to come into play here in a little bit. All right, so let's practice multiplying some complex numbers again. And I think I had said number 14 or number 16. Okay, so let's take a look. We'll do number 14 first. Number 14 says negative 5 plus 3i times 2 minus 3i. Well, again, this lesson, I really like how the end of the chapter is actually quite refreshing, because you already know what to do. You have multiplied binomials before. We can simply FOIL or distribute, because we're just multiplying binomials. I'll write it out the first time. So the first times the first, then the outermost terms, then your innermost terms, and your last terms. And now simplify. Combine like terms. And then don't forget, I squared is exactly the same as negative 1. And if we start with complex numbers, we're probably going to finish with a complex number, remembering to always have the real term come before the imaginary term. That's it. So I don't know if I need to do a second one where we are foiling. So as we're multiplying, let's practice doing a power. All right, so I will do 2 of these. So we're still looking at multiplication. As I said, this year, the highest power we'll get to is just a squared. So number 22 says 6 minus 7i squared. you already know what to do. When in doubt, write it out. And now use the distributive property or FOIL. First, outside, inside, last. Combine like terms. Remembering, of course, I squared is exactly the same as -1 by definition. So 36 minus 49, -13 minus 84i. So the highest power you're going to see this year is squared. Anything higher than that, in my professional opinion, we will use when we do polar numbers, and we'll do De Moivre's theorem in pre-calc. Okay. Now, what if, we're still same idea, just going to make it look different. 3 plus I root 5 squared. Now remember, the square root of 5 is still the coefficient. We're still multiplying. We just chose to put it after the I so that it doesn't look like the I is underneath the radical. So that's something I mentioned in the last lesson and I mentioned in class. So just write it out. When in doubt, write it out. Now use FOIL. Use the distributive property. 3 times 3. And then the outside term. Inside term. Last term. I times I is I squared. Root 5 times root 5 is 5. Three i's and 3 i's are 6 i's, root 5. -1 replaces the I squared. Okay? So we end up combining like terms. So we've handled addition, we've handled subtraction, we've handled most of the multiplication. We're only 20 minutes in. So what took us 7-8 years to do in elementary school with real numbers has set the foundation for the imaginaries you did last time and has also set the foundation for complex. This is why we spend so much time in mathematics setting up the foundation. Now we're going to take a look at division. Now we've done division. We have divided whole numbers, fractions, decimals, radicals. So let's take a look at imaginaries we did last time. Let's take a look at division using a complex number. So, I'm going to start off with, We'll start off with number 32. Now, last time we talked about how to divide when it was a pure imaginary number. Now we're going to take a look at how to divide when it's complex, meaning it's a binomial. So there's two parts. Well, because we have an I in the denominator, we have a square root of -1. We're not allowed to have a square root in the denominator because it tends to be irrational. So what we're going to do is, because we have two terms, we're going to use the conjugate. So instead of multiplying by 1 plus 7i, we are going to multiply by the number 1, and we're going to make it its conjugate. 1 minus 7i. So that's the complex conjugate pair. It's complex because it's got the I in it, and it's still a conjugate. After you practice this over and over, you'll see what the shortcut is. I don't care about shortcuts, just multiply it out. Our numerator is going to be 10 minus 70i when I distribute. The denominator, when we quote FOIL it out. First term, 1 times 1. Outside term, negative 7i. Inside term, positive 7i. Last term, 49i squared. 10 minus 70i. The beautiful thing about conjugates, they automatically cancel out the middle terms. The inside and the outside automatically cancel. So we're left with 1 minus 49. But remember, I squared is the same as negative 1. And this is where we always said the product of complex conjugates always leaves the sum of squares. So that's how I got the 1 plus 49, coming from this 1 plus 7i. So this is 10 minus 70i over 50. Okay? But if you turn it in as that fraction, 10 minus 70i over 50, it will be wrong. It will be wrong. The reason it's wrong, and some of you are like, oh, I can reduce. Yes, you can reduce by 10. So let's say you reduce by 10, right? All of them divide all three of them by 10, so you get 1 minus 7i over 5. That's better, but it's still wrong. Now, if you're looking perplexed right now, kind of like, what? But I factored a 10 out and I reduced. You're correct. We're not in the real number system. It started as a complex number, which means it needs to end as a complex number. A complex number has two distinct parts, a real part and an imaginary part. So if you're left with one fraction, you must pull it apart. You must separate this. You must pull it apart and have a real part and an imaginary part. So if I pull this apart, the only way they could have been combined together is if they both had had a denominator of 5. 1/5 minus 7/5 of an I. And now I have a real number part, 1/5. I have an imaginary part, negative 7/5. Now we're finished. So it's got to be two distinct parts, a real part and an imaginary part. So that's where some of the little subtleties, okay? Remember, these are all similar, but they do have different, specific, unique qualities. Okay. We're looking good on time. So let me look at 36. Because the others are, you know what a reciprocal is. You know how to do substitution, so I don't feel it's necessary to show you a reciprocal, because you know once you take a reciprocal, then simplify. Let's try one more of these. So we'll finish off with, what did I say, 36. Negative 3 plus I root 5 divided by negative 3 minus I root 5. I could have put that in a word problem. It says, find the quotient of negative 3 plus I root 5 and its reciprocal. Now think of this. Find the quotient of -3 plus I root 5 and it's, conjugate, not reciprocal. So I could have put that in words. So we would be dividing -3 plus root 5 and the conjugate of that. All right, let's do it. Well, if I analyze this, I cannot divide by an I because it's the square root of -1. And look at that, I cannot divide by root 5 because it's got a square root. So either way, we've got to use the conjugate. So I'm going to multiply by -3 plus I root 5. Let me rephrase. I'm going to multiply by the number 1. I'm just making number 1 be the conjugate of the denominator. Okay, you do it, I'll do it. We'll FOIL these out. We'll see if we get the same thing. I'm just foiling. Now hopefully you got to where I am, 4 minus 6I root 5 over 14. But then you recognize, wait a second, we have complex numbers here. So we have to pull it apart to the real number part and the imaginary number part. Now treat each fraction as its own, reduce each fraction. And there you have it. 2/7 minus 3 root 5I over 7. Now you might see it listed this way. 2/7, and then they might put the 3 root 5 together because that's technically the coefficient. Just make sure that that I does not show up under that radical sign. Okay. That's it, guys. The rest of it, I think, has a little bit of vocabulary, but you already know what conjugates are. You already know how to do a substitution problem. So try those, see how it goes, and that brings us to the end of Chapter 6. So until I see you next time, have a great day.